Now, can you treat this How do you treat the decoherence? What are the sources of decoherence? Well, you can think about this quasi-classically. And there are two things you can think about, one of which is line broadening due to the Stark shifts that result from the noise. These are the energy levels of the Stark shifts, Stark energy levels, when you have noise present. If you have no noise, you just get these energy levels. But now when you introduce noise, you get additional energy level shifts governed by K. And since we have a random distribution of initial orbits, we have a broad distribution of values of K. So this means that you now get a whole new range of energy spacings, which are just taken by dE by dN, gives you the frequencies that correspond to those energy spacings. And you now then get additional terms of 3/2 Kf. Okay? And they depend on F. So what you have to do is you now have to quantize that original classical distribution along a whole set of new quantized levels. You get a whole set of new evolution frequencies. Okay? And this is illustrated here. As you increase the strength of the field, the levels you get broader. And ultimately you get a quasi-continuum. Okay? And this is a broadening mechanism that is independent of frequency. It's governed by the strength of the field that you apply. The other source of broadening is because you have field steps. When you apply a field step to an atom, there's a probability of it undergoing a change in its N. Okay? So what happens is the transitions in the noise frequency induce N jumps. And these you can model by a random walk in N. You just say as time goes by, the number of N levels I have broadens. Okay? Now, how do you get the rate at which that broadening occurs? You can do that by using just regular classical theory. You start out with a series of discrete levels, and you just see how they broaden classically as time goes by. And then you just discretize that final distribution of energies, and that's told you how my initial one evolved to my final one. That tells you about the diffusion. And here are the results of theory. If we only consider the decoherence that's due to the Stark broadening, you would get, as a function of strength of field, you would get quantum beats that look like this. They don't depend much. If, however, you include all that evolution, the transitions in N, the broadening of N levels, you see that these revivals rapidly go away. Okay? So the dominant source of decoherence here is jumps, transitions between different values of N. Does the theory work? Yes. So here are the results again with experiment using noise of 50, 250, 450, and 1250 megahertz of amplitude 100 microvolts per centimeter. Okay? Here's the experiment, here's the theory. 50 megahertz, looks pretty good. Go to 250 megahertz, where the noise characteristic frequency is the order of Kepler frequency. We don't see much in the way of quantum beats. Theory doesn't predict much. But if you go higher in frequency, then you see that they begin to reappear, and that is indeed 1.25 gigahertz. That is indeed what theory predicts. So there's good equivalent between theory and experiment. Okay, now what I'd like to do is to shift gears slightly and ask the question, well, we've been able to produce ball-like wave packets, but they were transient. They subsequently spread out. Can we actually create non-dispersive ball-like wave packets? Can I make a localized wave packet, and can I keep it localized? And the answer is yes. You do it with a protocol like this. You start out by exciting a quasi-one-dimensional state in a DC field, which you can then turn on. Then you apply a pump field to make it into a circular state, and then you wait until it localizes, and when it's localized on the plus Z axis, you start a series of kicks towards the nucleus, whose period is exactly the same as the orbital frequency. And at the same time, you apply, as you start giving these kicks, you apply a little offset so the average field that the atom experiences is 0, and you don't get any Stark precession. So now then, what happens when you do this? So we start out, remember, this is what you would get in the absence of a drive field. After you turn off the pump field, you get this localization, so you get a localized wave packet, but then it dephases, spreads out, and you lose the oscillations. Here's what happens if, at the time of optimum localization, you turn on the series of kicks. And you see strong oscillations and survival probability telling you that the state has remained localized and it's happily going round and round and round. Okay? And it does this for many, many hundreds of orbits. Now, you can maintain localization by driving it at the Kepler frequency. Remarkably, you can also do it if you drive at the subharmonics. If you drive it once every 2 cycles, or once every 3 cycles, or once every 4 cycles. Now, how does this work? How is it that we can actually get it locked in? Well, one way to do this is to consider a Poincaré surface of section, which I hope by now you're sort of somewhat becoming familiar with. And here's a Poincaré surface of section for n equals 306, using a sequence of pulses with 4.3 nanoseconds. Now, we're interested, remember, in an electron, in this case, that's moving in the xz plane. So if you want to take a cut in the Poincaré surface to get a Poincaré surface of section, it's sensible to cut the distribution at y and p sub y equals 0. In other words, it's moving in the xz plane, and it's not got a component momentum perpendicular to that. Also, we're interested in the circular state, so it's sensible to take a radial coordinate, which is x squared plus z squared to 1/2, which is equal to the radius of the Bohr atom. Okay? And then we can visualize this in the angular momentum phi plane. So this is the azimuthal angle, and this is L sub y. And what you see is you see islands of stability, these dark rings. Remember, we talked about islands of stability before. You see islands of stability centered on a particular azimuthal angle. These are for kicks of 1%. These are very weak kicks. 1%, the size of the initial electron orbit, 5%. Okay? You get these large stable islands, and you can localize a wave packet in these, and it will remain localized and be non-dispersive. Now, that's the hard way of picturing it. Physically, what actually happens? Well, it's much easier to think about it. We have a wave packet that's moving in a circle, right? And when it gets to here, when it's localized on the plus z-axis, we give it a kick in this direction, towards the nucleus. Now, the kicks we use are small. I was telling you, 1% of momentum, few percent of momentum, okay? So, that means that little energy transfer will occur. So the orbits are going to remain about circular. So as I keep kicking it, the orbits are going to remain about circular. What happens if I consider that part of a wave packet that is here? Well, we'll take this thing to be going anti-clockwise. Well, it's coming in this direction, right? So it has a component in the direction of delta P. So when I kick it, it loses a little bit of energy, delta P sub z, delta P, right? So what does it do? It drops to a lower end state. Its orbital period picks up. So it was originally a little bit behind in phase. It hadn't quite gotten here. But now it's dropped to a lower state, so it's going around faster, so it catches up. What happens if you're here? If we've got considered the bit of the wave packet that has gone past the z-axis. Now it's got a component in the direction of the kick. So now it gains a small amount of positive energy. So it moves to a higher end state, and its orbital period becomes slower. So it tends to move back into phase with the kicks. Okay? Now, this mechanism then just means that the kick can sort of shepherd the exterior of the wave packet and keep it localized and keep it locked in phase. Okay? So it stays locked. Now, clearly, this mechanism will work if you kick it every second period, every third period, every fourth period, whatever. So it works remarkably well. Now, the problem is we would like to take our circular state at n equals 300 and move it up to n equals 600. But what I showed you previously was that the motion of the wave packet was locked to the drive field. If you start modulating the drive field, if you start chirping it to lower frequencies, you would expect that it would stay locked. It would move to higher values of n. And in fact, it does. The problem is, as you kick towards the nucleus, there's very little transfer of angular momentum. So what happens is you march up to higher n, but it doesn't stay a circular state. It becomes ever more elliptical. Now, you can solve that problem by locking it into a sine wave driving field. So the protocol we use is, here's our pump pulse. We take a quasi-1D atom, we pump it, we try a pump, we make it circular, we let it localize, and then we start driving it with a sine wave at the Kepler frequency. And what you see, if you don't do that, is again, you get this transient localization of the wave packet, then it spreads out, delocalizes. When you start kicking it, at the time of optimum localization, you see strong oscillations, meaning strong localization for long periods of time. Okay? So the state remains locked to the drive frequency. And this was pointed out by Eberle and Stroud and many others. You produce what is in fact an analog of the Jupiter's Trojan asteroids. The wave packet forms an analog of Jupiter's Trojan asteroids. Now, what are Jupiter's Trojan asteroids? Well, if you look at the Sun-Jupiter system, then in a rotating coordinate system, so this is in a rotating coordinate system, then there are 5 points where you have potential minima. There's one here between Jupiter and the Sun, one on the other side of the Jupiter-Sun line, one over here on the opposite side of the Sun, and 2 over here. Now, you're probably familiar with these. They're called Lagrange points. Okay? Now, the Trojan asteroids of Jupiter are actually located at the L4 and L5 Lagrange points. You can trap asteroids in these points. Now, this is a rotating coordinate system, so as time goes by, these Trojan asteroids will go around with Jupiter, about 60 degrees ahead and about 60 degrees behind. And if you take a picture of what is known about asteroids in the solar system, you get something like this. Uh-oh, it doesn't show it to me. But basically, these are the various regular planets, and the dots here and the dots here are the Trojan asteroids. And you see they're locked 60 degrees behind and 60 degrees ahead. This ring here is what you would normally think of as the asteroid belt. Now, it turns out that originally they were called Trojan asteroids because when they were first discovered, they were named after prominent figures in the Trojan-Greek War. So these were named after Trojans, these were named after Greeks. But now it's known there are hundreds of thousands of the damn things, so the naming system doesn't work. But there are many asteroids found in these 2 locations, okay? Interestingly, there was an article just recently that said they discovered a Trojan for the Earth. So finally they discovered some similar asteroid that's locked in to the motion of the Earth-Sun system, which is kind of interesting. Now, you produce similar stable points in an atom by using a circularly polarized drive field. I mean, obviously, here this system is done by gravity. There's a gravitational attraction from the Sun, there's the gravitational attraction from Jupiter. Here we've got a Coulomb attraction to the nucleus, and you can replace Jupiter by a circularly polarized drive field. Okay? Now, we don't actually use a circularly polarized drive field, we use a linearly polarized drive field, but that has 2 counter-rotating circular components. And as the wave packet goes around, it locks into one, the other one averages to 0, sort of rotating wave approximation. Okay? Now, since the wave packet is locked to this rotating component, you can transport it to higher n by chirping the drive field. So what you do is, you say chirp it from a period of 4.3 nanoseconds to 34 nanoseconds over 1 microsecond. And here is the calculation showing how the energy distribution depends on time as you do this. And what you see, the energy distribution is it remains narrow and it moves up to higher values, in other where it's higher n. And you transport from about 300 to 600. I've not shown it, but if you do the theory, the L distribution also remains narrow and moves to very large values. So you're able to create a very high localized circular state. You're just sort of marching it out in a circle. Okay? Can you actually do this? And the answer is yes. You can confirm everything I've said experimentally. So we start out at t equals 0 with a transiently localized state. which is orbiting, in this picture, a relatively small radius. This is our initial state. We lock it to a dry field, and you see if you look at the survival probability, it's undergoing strong periodic oscillations as it's moving around in its orbit. We start chirping it, and at late times we've gone down to a low frequency. We're chirping down to 31 megahertz. We've taken the state to n equals 600. And if you look at the time evolution, you still see these strong quantum beats, meaning it's still localized. But you see the period is dramatically increased. And if you look at a picture of what the wave packet looks like, it's localized, and you see it's moving around in much larger radii than it started. Have we really transported to higher end states? You can check that by field ionization. So what you do is, here is the field ionization signal as a function of the applied field. With no chirp when we start out, this initial state at n equals 300 ionizes over a distribution of relatively high fields. As we go to higher end through the chirp, you see that distribution moves towards lower field, higher end, and it stays narrow. Very few states remain. We really have grabbed essentially all our Rydberg atoms, marched them up to high end. And if you finally chirp to 31 megahertz, you see you've got a very narrow distribution of high states. So it's this way of going to high states and manipulating, winding up the wave packet is superior to the chirp half-cycle pulse, because you can actually transfer angular momentum. Okay, well, it's time for conclusions. I hope I've convinced you of a number of things. Using carefully tailored pulse sequences, you can create near-circular Rydberg states, near-localized circular Rydberg wave packets, and you can manipulate them with remarkable precision. Now that would enable us then to say, start out with two n equals 300 atoms at some separation that don't interact very strongly, then wind them up to n equals 600 or something, where they will interact very strongly. So this provides us a way of tuning the interaction between Rydberg states, just using a few field pulses. Okay? Also, I hope I've convinced you that we can input and read out phase information into near-circular states, and that this can be recovered, as I said, using Fourier techniques. And the other thing is we have a way of probing decoherence and dephasing in a mesoscopic quantum system. As you know, people are talking about mesoscale systems now for quantum information processing. So it just shows you that you really can, in a quasi-2D atom, exercise remarkable control, and we hope to exploit that in the future to control the interaction between Rydberg atoms. Thank you.